Okay, hi everybody. Before we start, may I ask if you please turn on your camera, those who can. Thanks. The more the better. Okay, so today plan is to continue the discussion that we had last week. If you remember, we went through the instructions cycle to these 6 steps, and we discussed how each of these 6 steps is going to execute it on the machine, and some details specifically connecting this with the data path in the microarchitectures, what's going on down there when we execute a particular instruction on the machine. And today, the plan is to go into some more details, specifically talking about the ISA instruction set architecture, more or less making some generalization over what we have discussed so far. Before we start, do you have any question? So about the quiz, we are going to release the grades hopefully soon. There was a small issue with the auto grader in Gradescope. So I found out there are some grades were incorrect. So we need to correct the grades, and we'll release this grade soon, hopefully. Okay, if there is no question. Oh, by the way, some of you actually did not submit the quiz. Hopefully there was no mistake from our side or your side.
I had an issue with that. Like, I submitted my quiz. I can talk about it after class. I don't want to take too much time. I was just saying I did the entire thing, and then it said I didn't submit it like several days later. So, and I did submit it. Like, it told me I submitted it. So I wasn't sure what happened, but I could talk about it.
Yeah, Nora's told me about that. Hopefully we can correct it. So no issue with that. Something went wrong probably in the system. There were a few actually 10 of you who did not submit. So hopefully things become better from next time. Okay, let's start. So essentially, if we want to summarize the instruction cycle or the control of the instruction cycle as a state machine, this is how the state machine looks like. So I'm not sure whether, how many of you know about finite state machines? Hopefully you know. Can you confirm whether you know the concept behind a finite state machine? Yeah. Okay, some of you do not know, but I presume in 211 you should already know. But essentially, a finite state machine, maybe let's go before we discuss this. Finite state machine is a discrete time model of a stateful system that we have like in our machine. Each state represents a snapshot of the system at a given time. So essentially, each finite state machine is somehow a representation of the state of the system and the transition between states. So it consists of states and transition between these states. So for example, you can model essentially like many different systems with a finite state machine, for example, a traffic light, elevator, fan speed, microprocessor, and many other things. And I think I have also an example here. For example, this is a finite state machine consists of 4 states, A, B, C, and D. So you see that the system from a state A only can transition to a state B, not C and D. So the transition have particular semantics showing you what would be the next state that the system can transition to from any particular state. And essentially, this is the simplest way that you can think about a finite state machine. There are more detail. Hopefully, you should already know that from 211, specifically when you learn about sequential logics, this is where basically you needed to understand or use finite state machine in order to understand sequential logic and how the memory works. But I'm not going to cover that now. So essentially, wanted to remind you about the definition of a finite state machine. At the fetch state, this was the first step in the instruction cycle. If you remember what happened, this is essentially the first state where the machine is on, right? So at the first state, the content of the PC is loaded to MAR, and also the content of the PC is incremented by 1. We discussed in detail last week about this. So this is in more detail what's needed to happen. Basically, in the finite state machine, there is an assert that change the gate PC and load MAR, or essentially send this control signal, and also it selects the +1 in order, and also assert load PC in order to increment the content of the PC by 1. We discussed about this before, so I'm not going to elaborate more than that, but hopefully you can recall what I'm saying. So this is the first step. The next state would be going to load the basically what is in the MAR memory address register, and put it in MDR memory data register. Essentially, at this state, the encoding of the instruction that is located at the location PC in the memory would be loaded into the MDR. So you have the encoding, or you have the encoding of the instruction already in the MDR, where you can go and decode it. This is what you needed to decode to see what the instruction is about. And the next state would be putting the content of the MDR memory data register into the instruction register in order to basically decode this instruction. So this is the 3-step, which here we model it in the finite state machine only from the fetch stage of the instruction cycle. And you know that the next stage would be decoding. So once you have the content of the instruction in the IR, you need to decode it. What's the particular instruction you want to execute? So you need the opcode. From the opcode, you can decode what's the instruction. This is the state 4. Once you decode the instruction, depending on the particular instruction, the finite state machine would transition to different state, depending on the particular instruction. If this is add, would go to the left. If this is LDR, down there, and if it is jump, at the right state. So depending on what instruction it is loaded to the IR and what is in the opcode of the IR, the state transition would be different. So if we assume that this is a jump instruction, then in jump, you know that we need to jump to a particular place in the memory, or putting the particular memory address, loading it to the PC in order to move the PC into this new particular location where it is instructed in the jump code, jump instruction, as you remember. Once this, for example, this is state 63. Once this is executed, the system, the finite state machine would transition to a state 1, go up there and basically execute the first step of the fetch, on and on. As you remember, this is a cycle that the system would go through until everything is done. Is that clear? So this is the partial view of the finite state machine, which is defined by the designer of the machine. This is LC3. The designers of LC3 designed this finite state machine. The way how the machine actually get executed and go through these states until it's you turn off the machine, essentially. I'm not sure. One of you need to mute yourself. I hear a noise. So I skip. And this is the full view of finite state machine of LC3, which you see here. All possible instructions that has been defined in LC3. You see LDR, SDR, not, and add, and all other instructions which have defined for this particular machine. And you see that like many different state states that the machine would transition to, and how this looks like. So now let's discuss a little bit about ISA, instruction set architecture. We somehow at the beginning of this course, the first lecture, we discussed about it. So instruction set defines the opcodes, the data types, and addressing modes. For example, we have add LDR. We defined this previously, so how they look like in the encoding. You have some opcode, you have data destination register, you have source register 1, source register 2, and where are these located in the encoding, right? LDR, the encoding was different, right? So you had one offset, you had base R, you had destination register, and you had 6 bits of, sorry, you had opcode as well. And you had 2 different encoding for 2 different instruction in one machine. And this is essentially one part of the ISA, the opcode, the data types, and also addressing mode. For example, in add, the addressing mode was based on register. It's called register mode. In LDR, you had the base address is where the base R is encoded, and you needed the offset. This is where you see offset 6, and you add them together in order to find the address that you need to load the data register, the content of the load the content of this particular memory address into the destination register. So the addressing mode, depending on the particular instruction, would be different. And type of addressing mode, what kind of addressing mode we have for each particular machine is part of the ISA, part of the instruction set architecture. And if you think about it, the ISA, we discussed this before, is a sort of contract where enables the connection between the high-level stuff, the program level, where the programmer defines or write programs, to the low-level stuff, the hardware level components, microarchitecture circuits and electrons. So the ISA is a contract that defines this connection. So once we have this contract, the programmers know how to write programs, how to combine these instructions to implement the program that they want. The hardware part also knows that how to implement these instructions with the logic gates. So since we have a finite set of instructions, implementing these with the logic gates, it's straightforward and it's fixed. So with this contract, the hardware part needs to only implement this finite set of instruction with the logic gates, and both layers could talk with each other without basically any worry that what would happen, whether the program that I would write with these instructions would be able to get executed on the machine, because the ISA would make sure that these connections would happen. So that's the position of the ISA. It acts as a contract between program level and the hardware level, the macro architecture. Or in the other hand, like you can think about macro architecture as the layer that implements the ISA, and program as a layer that use the ISA in order to write a program. That's the way how you can interpret these different layers. So the ISA specifies the memory organization, like how much memory we have, the memory address. In LC3 we have 16 encoding, so we have 2/16 memory addresses. In MIPS we have 32-bit encoding, so we have 2/32 possible. Like this is how large the memory is. We have addressability. We have we discuss about word addressable or byte addressable. Before, the set of register would be different depending on the particular machine. In LC3 we had 8 different registers, R0 to R7. In MIPS we have 32 number of registers. And also the instruction itself is part of the ISA. The whatever it is encoded in the opcode, the data types and the addressing modes. So when somebody asks you what is ISA, at the abstract level, you can say this is a contract that enables this connection. More clearly, ISA specifies the memory organization, register set, and instruction set. So let's go into detail of each of these parts. Already we discussed about each of these, but we now make it more concrete in some other way. But we discussed about opcode before. Somehow these opcodes really depends on particular machine. Some opcodes could be very basic, like and or add these basic instruction. Some opcodes could be very complex. Some instruction could be very complex. So for example, in HP ISA, we had an instruction to do A multiply B plus C. This was one particular instruction in the ISA. In x86, like we had MMX as instruction, so we have more complex, like for multimedia kind of instruction in VAX, which was kind of popular machine like many years ago in 70s. It had like way more complex instruction than comparing with the other ISAs. It had, for example, an opcode to save all information from one program before jumping or switching to another program. That was like one very complicated opcode in this particular ISA. And if you search for it on Google, you will find documents defining the different, typically very complex instruction in this ISA, comparing with what you have already seen in MIPS, for example, or LC3. And there are some reasons for that, this difference between complexity, and this trade-off is somehow, also we discuss about this trade-off. It, it, it really depends where we want to put the ISA. Like if we have complex instruction, meaning that the job of programmer would be a lot easier. They can write their task with less number of instruction. So since these instructions are complex, so for example, for doing any type of task, they need to put together a simpler number or less number of instruction in order to accomplish the task. But if the, on the other hand, if the instruction are very basic, like and, or, jump, this simple instruction that you see in MIPS, the programmer needs to write many different lines of code. If we like define complexity as a line of code in order to get the task done. But on the other hand, if we look or think about it from the hardware perspective, if the ISA has complex instruction, we need to put together a lot of or more logic gates in order to implement these instructions. So the hardware complexity would be, the hardware become much more complex. If we have basic, very simple instruction, implementing it with the logic gates would be a lot easier. So we have way less complexity in the hardware level. So that's defined this trade-off. And there are different trends in industry and different discussion, because it affects not only the burden or complexity from like hardware side or from software side, it also sometimes affects performance as well. So for a special purpose application, like for example, machine learning, now the trend is to like implement hardware accelerator specifically for machine learning or for some other task where you need highly parallelized machine. But in general purpose computer industry, the trend is to have instructions where the instructions are simple, as simple as possible. So you could write, so you could implement the hardware with low cost. Because on the other hand, all of these, when we have complex hardware, it means that we need to increase the cost. With simpler instruction, we have simpler machine and it costs less. Now you need to have like good program transformations that is happening in the compiler in order to compile high-level program into simple instruction that is defined in the ISA. That's what's happening in the in this trade-off space. Is there any question here so far? So hopefully this trade-off space is clear. In LC3 and MIPS, there are different or three particular type of opcode. And we had some example from each types before. We have operate, like add, and so on. We had data movement, and we had control, like jump. So we had examples of this before. So at the high level, at the general level, we have these three different types of opcodes. And we have,
Hey,
yeah,
can you hear me?
yep,
I do have a question about the last slide.
yep, go ahead.
So you're saying there are trade-offs between hardware complexity versus software complexity. I can see that, why that would be the case. But could you explain a little bit more about what having more complexity does to reduce the quality? I can imagine, for example, that a more complex hardware is going to be more expensive. It's probably going to take more energy. What are the downsides of more complex software?
I'm not sure whether I understood more. What do you mean exactly by more complex software? Or maybe you mean more complex instruction set, right?
Sure.
Yeah, so when we have more complex instruction set, one, I mean, like beyond the cost, because we need more complex logic gates, it could be a waste of these costs as well, right? So imagine that you implement a very complex instruction, but in 95% of the program that you write, you're never going to use this instruction at all. Only 5% of program may need this complex, like fancy instruction that save all the information of a program, to some register, right? And you maybe spend like a lot of money on like implementing this fancy instruction with this in your macro architecture, but nobody uses it, or like only few program uses it. It's just waste of money or waste of resources. It may, like in 5% of the program that you write, maybe yeah, it's useful, but like you should think about the whole trade-off space. And that's why, for example, very complex machine like VAX ISA disappeared, right? So and they're not around anymore, right? So we had some implementation of this ISA like in 70s, but they're not around anymore. And this type of complex ISAs would not survive over a long period of time, specifically when the usage of complex instruction become obsolete, right? So for example, at some stage, we may see that, okay, in a lot of programs that we write, like we need these particular operations. And like people say that, oh yeah, let's create a new ISA, and like let's have a new ISA and put this complicated fancy instruction there because it supports 90% of the current program. But like 10 years later, like due to advancement in compiler program transformation, people figure out that, okay, no, you can like execute this program by transforming this into like many different easier instruction, and then you don't need that fancy instruction in your ISA. You can reuse other simpler instruction instead, using this automated program transformation.
Okay.
And then nobody uses this instruction, complex instruction part of the ISA or your machine, and the cost of implementing that instruction would not be justifiable, right? So like company would not implement this ISA anymore, because like if like 90% of the program do not use this instruction or like set of instruction, like why I should pay money for building them. So that's a kind of way of thinking you can think about it. But like if you have like very basic simple instruction, there exists always program that you can transform and reuse this simple instruction in your program, in most programs. But now, like for example, since machine learning is very popular, there are a lot of hardware accelerator exploiting particular architecture. Is called systolic arrays, which has been invented like many years ago, but now became much more popular due to the benefit that this type of architecture provides, for example, for matrix to vector or matrix to matrix multiplication, which are the backbone of machine learning type of systems. A good question. Thanks for asking.
Thanks for answering.
So this is part of the ISA of LC3. You see all of these instructions. So this is the instruction set of LC3. This is not obviously the whole ISA, but only the instruction set of LC3, which you see here, bunch of different instruction and their particular encoding. Again, we went through only few of them previously, but you have again 16 different instruction in LC3. And in LC3B, the extension of this, there are some new instruction that appear. So LC3B is an extension follow-up ISA for LC3 machine. And this is for MIPS. So in MIPS, you remember we had 6 bits for the opcode. So this is the this is part of the ISA for R type of instruction. So in R type of instruction, you remember you have opcode of all 0. And this means that you should refer to the func type of func part of the encoding in order to find the encoding of instruction. So in R type, that was the encoding. So here you see like several different instruction: shift left logical, shift right logical, jump, register, break, whatever. We have so many different even R-type instruction, but you know that we have I-type and also J-type as a part of this this ISA, MIPS ISA. For example, we had discussed add before. You see on the first row, add in the func is encoded as 1, the rest is 0 or 32. with destination register, source register, and so on that you already know. As a part of the ISA, you have data types, right? So an ISA support multiple data types. LC3, for example, support 2's complement integers. MIPS support, beside 2's complement, support unsigned integers and also floating points. So again, the data types are important part of the ISA definition. And again, here trade-offs are involved. Some ISA, obviously, if you support less type of data types, your hardware implementation become easier, more complicated, or more variety of number representation or data types become way more complex at the hardware, but provide opportunities for programs, for writing efficient programs or programs more efficiently. And we know that like you can encode all of these in the software. Like this is the way how it works, right? So you have some basic representation at the hardware level, or ISA would allow you to have some basic representation. But in order to have more complex, so for example, if you want to have a linked list or hash table or like more complex data type, you obviously can implement them at the hardware, at the software level, right? So, for example, you could define like linked list with basic data types that you have at the hardware level. Obviously, if you could implement some facilities, as I mentioned, like for example, for machine learning, if you could enable matrix multiplication at the hardware level, since hardware is a lot faster than the software, whatever, like if, for example, many of the program that you write use matrix multiplication, and if your hardware support that, obviously it becomes a lot, when you execute it on the hardware, becomes a lot faster because it's the hardware running your code. You can obviously define matrix multiplication in your software using basic data types in the hardware, right? So your hardware implementation becomes a lot easier, cheaper, less complex, but has the downside that like it needs some transformation, it needs some reusing, and it's not as fast as if it were defined in the first place at the hardware level. That's again the trade-off. This time for data types. Previous time we discussed it in terms of instruction. Now is in terms of data type. So in both aspects we have trade-off, right? Hopefully this is clear for you, because essentially this trade-off space is one of the most important part of the computer architecture, and you see it everywhere, right? Because it's really important, and if you think about it, there are reasons for being important. Again, think more broadly, right? Think about the application, right? So you want to have a computer that supports like a lot of variety of applications, right? You can like write from simple data manipulation to machine learning to, for example, collecting sensor data to doing scientific calculation, so many different workloads, right? But sometimes you want to have a very special purpose computer where you only want to run for example, scientific workload or only machine learning workload. Then all of these trade-off becomes very important, and this is the job of computer architect to reason about this trade-off and make the right decision. And for you, it's also important to understand this trade-off space. So when you become in charge of designing a new computer, or at least in order to understand this new computer, you will see the justification for that. You will see why this decision has been made. Or you can make a sense out of this, or like you can exploit these features, like if you know this trade-off, right? If you see like opportunity of exploiting particular instruction in the ISA for accelerating the program that you write, this is what differentiates you from like the rest of the programmers, right? Because you know down the line what's going on, right? So if you understand full stack, not only at the software level, if you understand how the program that you write would get executed all the way down from program to ISA to microarchitecture to logic gates, you can write a better program. You can write your program much more efficiently than the other programmers that maybe they only know, like for example, Python grammar, right? They can write only in Python, and they don't care about like how this Python code that I wrote gets executed on the machine. That's somehow what differentiates those programmers who knows computer architecture and is hardware side of thing from those who do not. And that's why it is again important, wanted to emphasize on this trade-off space. Yeah, and essentially this is about this semantic gap. So basically, this exactly the same thing that I mentioned. So if the ISA become more complex, the semantic gap between program and the ISA become smaller, but the semantic gap become larger if your ISA becomes simpler. But you can fill this semantic gap with program transformation, compiler stuff. And that's why, like, this trend in industry, like RISC versus CISC. RISC is reduced instruction set computers. Is the trend that basically happened like with the early ISAs and architectures. CISC is complex instruction computers, and like this risk now become more mainstream these days after this type of mindset happened in computer architecture. So that was the data type. So far we had operation, also data type. Now addressing mode. Addressing mode is also a mechanism for specifying the where the operand is located, right? LC3 we have different addressing mode. Particularly we have 5 addressing mode. Like immediate is an addressing mode that is encoded in the immediate as a constant. You see this immediate in assembly code, right? What the constant is defined in the assembly code and is encoded accordingly in the encoding part as well. It could be register. The operand is one of these 8 registers that you have. And it could be like other type like PC relative, indirect, and base plus offset. We saw, for example, base plus offset in one of the instruction that that we reviewed. Hopefully you remember which one. LDR, right? In MIPS, beyond these 5 addressing modes, we have also pseudo direct addressing, in particular for J, and which was for jump and link. But MIPS, for example, doesn't have indirect addressing. We have not discussed indirect addressing, but we will at some point. So this is all that you needed to know about this part of the ISA. Do you have any questions so far before we move on to the operation instructions? Let's beyond this now. So now we hopefully you got some understanding of ISA itself, right? So far we have discussed, or we somehow formalized. We discussed for the multiple times what is ISA, but now you know, after you have a notion of this instruction, you have a notion of the encoding. We somehow generalize it a little bit to see or to get a better understanding. When we say ISA, what is in the ISA? And you can look at different ISA, and this is what I would recommend. Maybe like Google for VAX ISA. See what you find out in the document, right? Or like X86 ISA, right? And look at what you can find in the document. And you can see that all of them are the same. You find the same thing, right? You find basically pretty much what we discussed. You find about addressability, addressing mode. You find about like data types, right? And you will find about like this instruction encoding. So this is what you find, and plus some description of like each instruction, and maybe some examples how we can write programs with these instructions. This is like what constructed an ISA, no more than that. and all of them pretty much are the same. Now let's go inside more detail. Specifically, let's have some discussion about detail of this instruction. We start from operate instruction. In LC3, there are like 3 operate instruction. We have not is a unary operation. Basically execute the bitwise not. We have binary operation, add and AND, where it requires 2 operands, and is a, for example, bitwise operation between like source register 1 and source register 2. Add is a 2 complement addition. You know that, like how to do the 2 complement addition. In MIPS, there are much more operation, as you know, due to higher complexity of MIPS comparing with the LC3. We had R-type, most of which require binary operations, like adding, and, NOR, XOR. You're familiar with these. We had like I-type, where I-type was the immediate instruction, right? You had immediate operand, and you have this floating point operation where we did not have any examples so far, but we will discuss later on. So, for example, not in LC3, this is how it looks like. You have the first register specify the target, and the second one specify the source. Basically, we want to note what is located in R5, register number 5, and put it in R3. And these are the encoding, particular encoding. So you need only the opcode, destination register, and source register, and the rest is not useful, at least in not. This is how the machine encoding look like, and this is what you need to implement it at the logic gate, right? Again, this is a partial view of the LC3 machine. You know where it is located. This is only thing that you need to execute the NOT, right? So you have the source register. You know where exactly it is located in R5. And the logic gates for NOT is located in arithmetic logic unit. Obviously, ALU implements some other logic gates. NOT is one of them. You need to know how you need to tell ALU that I want to execute NOT. Obviously, this comes from your finite state machine. So again, back to finite state machine, how you could find out about what exactly, what instruction you want to execute. Like, this is obvious coming from your opcode, right? Your opcode encodes or tells machine what instruction you want to execute. In this case is not, right? So one input is coming from the source register. here you tell ALU that I want to execute not. And again, to make it a lot clearer, let me remind you about remember this. So here you had finite state machine. You basically, you remember about the whole cycle. You now have the encoding, particular encoding of the not instruction in the IR, right? In the IR, during the decode phase, you tell the finite state machine, you pass the decode, the opcode to finite state machine, and finite state machine tell your ALU through this link that what instruction I want to execute, right? This is what's happening from all the way from, and before that, you remember, like all the way before that from PC. From PC, you basically load, your PC locate to the particular memory address. You put the PC into MAR. From MAR, you loaded up this particular instruction, which happens to be not instruction, right? You put it into MDR, and MDR you put it to IR, and IR to finite state machine in order to decode it, and then the finite state machine tell ALU now I want to execute not, right? And the other one coming from source register. Then going back, so now here you have a partial view of the whole machine. So for a finite state machine, you tell ALU I want to execute not based on this opcode 1001. If this happens to be like something else, then and if this is basically this is of operation, then you may want to tell your ALU that I want to do add in addition to instead of not, right? So it really depends on your opcode. But if your opcode is 1001, then this is not. So your ALU needs the source operand and do the bitwise not to this source operand, and you put it here in the destination operand, destination register, which happens to be R3, which is encoded in the instruction. And you see that this is a bitwise not, and you put the bitwise not of the source register into the destination register, and you're done. Any question about this? Hopefully it is clear. So this was LC3, but in MIPS there is no not. There is no opcode, or there is no instruction for not. And you know that you can implement, or you can with the logic you can implement not with some other logic. Maybe think about it, how you can implement it. Implement not with some other logic, but if you do the math, you will realize that it's not difficult. You need like nor in order to implement not. So you can do nor of your operand with itself in order to implement not. So that's not difficult with some refreshing of your mind with the whatever you have learned in logic, you realize that you can implement with some other logics. Okay. What else? So we have also, is there any question? There is something I'm missing. How is SR001? Let me see. I'm not sure whether I can follow your question. Can you, Ross, can you verbally ask your question? Because I'm not sure whether I understand it.
Yes, sir. So the byte code, the field is 001, which in binary is, of course, 4020, so it's just 1. How does that equate to 5?
Oh,
there's something
no,
I missed.
No, this is incorrect. Yeah, this is incorrect. This has to be 101.
Oh, okay. So it's just a typo on the example. Okay.
Yeah.
Okay.
Good.
Thank you.
Good catch. Yeah. Okay. So obviously, like we have add and AND in LC3, right? Like this is the encoding for the opcode for add 0001. Again, like you don't need to to be clear, like for anything, you do not need to memorize this opcode or whatever. If you are given any questions and so on in exam or quizzes or everything, we give you this encoding. You don't need to memorize any of this. The only thing that you need to learn is to how to do, like, for example, how to interpret this instruction, or understanding the semantic of each instruction. Right, so for example, the second line specify the semantic of add, and we discussed add before, right? You have one source register and you have one immediate. Again, this is add in LC3, not MIPS. You need to sign extend immediate, like your immediate is 5 bits. And your numbers are 16 bits. So you need to sign extend. So you cannot add like SR1, because SR1 is like 16 bits, right? And immediate is 5 bits. So you need to sign extend your immediate to 16 bits. So sign extending meaning that like immediate, if it is like the first bit or the most significant bit of the immediate is 0, you put 0 all the way to make it 16 bits. If this is 1, meaning that this number is negative, so you need to repeat 1 all the way down in order to sign extend this number. So that's the way how sign extension work. So you need to sign extend immediate in order to make it 16 bits. And then once you add it to SR1, then machine would put this add result into destination register. And is encoded like this, and the semantic is similar, but you do the and between these two numbers. Okay, and here is example. So you have add. So in this case, in the assembly code, you have R4. Basically, the content of R4 plus -2 would be added to R1. This is what this code is specifying. You have this encoding down here. And in immediate, hopefully you can interpret this, why this is -2. Can anyone interpret why it is -2?
2's complement?
2's complement. How we quickly figure out why it is -2? So it's you need to negate this, right? So you need to flip the bits and add 1. So that's -2, and you sign extend. So we repeat 1 all the way down to 16 bits, and you add it to 4, and you put the result into destination register. So in source register, you see that it is 4, locating to R4 in the register file. So you have 6 there, right? And you have your destination register into R1, so you know where to put the result there. So 6 plus -2 means 4, right? This is where you find out in destination register. From encoding, like 0001, the code will be decoded in the finite state machine and tells the ALU again back to the whole view. Tell the ALU I want to execute add. We know where the immediate is located in the in bits number 0 to 4. We extract that, we sign extend it, and this is where you see the sign extended number of your immediate, or your 5-bit immediate. And then here you have a mux to tell like which one of the input you want to select, whether the other input should come from the register file or from some other data path, right? So in this case, this is coming from immediate. So this bits would tell that this is going to be sign extended, and this sign extended of this immediate would go as the second input to your ALU, and your ALU execute the add of these 2 numbers and put the result back to R1, which is your destination register. So this is how it is executed in on the LC3 machine. Any question about this? Let's stop here. Or maybe let me quickly also, because we have only like, give me like 2 minutes. We also discussed this I-type, because that's the last one before the data movement instruction. And we had this I-type before in MIPS, right? Like, for example, load word is one of these I-type, right? Where it needs RT bits and also source bits, and also immediate. So, for example, add I in MIPS would basically, after sign extending the immediate and adding to source register, and put the result back to target register. This is very, very much similar to what we had in LC3. This is obviously the encoding here. We have 32 bits to encode the whole instruction. Is larger immediate, so we can support larger numbers here. And basically, this is the way how this is the semantic of this particular I-type in MIPS. But I guess I remember we have discussed this before. Also, like, subtraction is similar. In MIPS, for example, if you have this high-level code, like adding C to B and subtracting D from the result and putting the result to A, like, is 2 lines of code in MIPS. Like, we need addition and subtraction, and MIPS support subtraction. So here, like, we add S1 to S0 and put it to T0, and then we subtract whatever we had in T0, we subtract S2 out of it, and we put the result back to S3 as a result. This is what it implements, the high-level code on the left-hand side. In LC3, we do not have subtract instruction. Instead, we need to use not and in order to do the same. So essentially, we need more instruction. In this case, again, this is one other trade-off, right? And like, it's easy. You guys know, like, you can implement subtraction by adding and by using not, and you can transform the code into these 4 lines of assembly code in order to get the very same semantic of the high-level code. So here you see, like, one particular scenario where like, you need more lines of code in the case where you do not have a particular logic in your ISA. So your program become larger, right? But your machine implementation become a lot simpler, right? In LC3, like, the hardware is a lot simpler than MIPS. But on the other hand, in MIPS, it becomes easier, like 2 lines of code in order to implement this particular semantic that you see implemented in C. So that's a kind of trade-off that that is happening. On the other hand, you can think about it maybe like why we needed like subtraction if we why the designer of MIPS decided to have subtraction. And like that was the decision that was made by the designer of MIPS, but the key thing was that we need a lot of these operations, subtraction, in like many programs. And that's somehow true if you can think about it, like in like in many programs, data manipulation, scientific workload, whatever, databases, we need this type of operation anyway, and it's better to pay the cost and get benefit out of this implementation. But again, this is back to the trade-off space that we have talked about it. So let's stop here, and we'll continue this discussion about more detail about different type of instruction. More specifically, we'll continue on data movement instructions on Thursday. Hopefully, we should be able to finish this instruction. Once we finish the instruction at a high level perspective, then it comes to the place that we are ready, or you are ready to write some assembly program. Then we'll move on to programming to see to discuss how to write more complex assembly program, how to implement more interesting semantics, more interesting high-level code than like this like simple code. So to be able to write more complex program. I would stay here for a few minutes. If you have any question, would be happy to answer.
I was just going to ask about that that quiz. If there's, I mean, I